In this section, we will look at how the COMxL can be used to solve one-dimensional optimization problem. So in this worksheet, we have our optimization problem over here. It says L is to be compressed from 1 to 10 atm pressure in a two-stage compressor. To increase the compression efficiency, the compressed air from the first stage of compression is cooled before entering the second stage of compression gas. Gas at temperature T1 equals 300 Kelvin. Find the intermediate pressure P2, at which cooling is required to minimize the work input to the compressor. Also, calculate the minimum work required to operate the compressor. Aiming at an error margin of not more than 10%, use the exhaustive search method to determine the optimal compressor work. So now we have two compressors. So the air stream comes into the first compressor, that is compressed, and the compressed air outlet of the first compressor is being sent to a second compressor, where it undergoes a second compression and it comes out. So we have the in of the first compressor is out, that serves as the in of the second compressor, and then the out of the second compressor. So in here, the problem is asking us to solve for the minimum work that is required to operate the compressor, and the intermediate pressure, that is the pressure between the first and the second compressor. So the work done by the compressor can be determined by this correlation over here, that is W equals to K over K minus 1 out times RT1, and that term times this term in the brackets. So here the P2 is the intermediate pressure, the P1 is the pressure at the entry point of the first compressor, the P2 is the exit pressure of the second compressor, and the T1 is the temperature of the gas, the R is the molar gas constant, and the K is the CP ratio of air, and then for air, K of CP over CP equals 1.4. So if we feed in the known variables, we have the last equation here, W equals 1.009 times 300 times this term in the bracket. So the goal is to minimize this work done, to find for the pressure that caused that minimization. So we come into these cells. So we have this for our P1, so let's make here P3 rather. So we have our P1, that's the pressure at the inlet of the first compressor, and we have P3, that is the pressure at the outlet of the second compressor. The goal is to find the intermediate pressure, that is P2. So we write our work function as a function in terms of the first boundary, that is in this case the P1. So if it was to be x1, x2, where the x1 is the lower boundary, it would have been in terms of x1. In here we have P1 as the lower pressure, P2 as the maximum pressure. So the lower bound is P1 and the upper bound is P2, P3. So we write our work function in terms of the first pressure. So if you have to write the pressure, the work function, you say, so we start by bringing an equal to. So 1.009 times 300 times, we open the bracket, and we have P2. So we referring the P as the lower bound. So P over 1 power 0.4 over 1.4, I close that power, plus 10 over P power 0.4 over 1.4 minus 2. I close the main bracket, equal to. So I have written my objective function, that is the function for the work minimization. So in here we have several one-dimensional optimization solvers in the COMxL. So in this problem we are asked to use the exhaustive search method. So we will first employ our coding search method, our Fibonacci, and then dichotomous, and we come with the exhaustive search method. And we will also use the Newton-Raphson method to solve for this minimum work and the pressure at which it occurs. So if we start our coding section method, it will ask of the cell that contains the objective function. In this case, the cell that contains the work function, and that is the cell K6, this cell over here with the mouse on it. So we come into the cell, we select the cells, and it asks for the cell that contains the variable boundaries. So in here, the lower bound and the upper bound, that is the continuous cells P1 and P3. So I come here, I select the values of P1 and P3, and the output location, so where the output should be. So I'll put that one over here. So let's put the output of the golden section method here. So if we click on solve, so after 7 iteration, so it gives our minimum work to be 235.8055, and it occurs at a pressure of 3.124614. So this is the value of the B2. That is our intermediate pressure according to the coding section method. Now with that same objective function in the function boundaries, use the dichotomous set method. So it says select cell containing function. We select our function cell, select cells containing boundaries. And delta, we keep it at the normal delta. So output location, we select here and we click on solve. So from the dichotomous method, after 10 iterations, we have the minimum pressure, that is the pressure P2, and the work done is 0.1574 atm and 235.807 work was done. And if we use our Fibonacci search method, the same approach, select cell containing function, select cells containing function boundaries. The Fibonacci number, in this case we use 6. The output location, let's put the output over here. So according to Fibonacci's method, the value of the intermediate pressure P2 is 3.0769, and its work is 235.8263. So now let's go to the exhaustive search method. So cells containing function variable, cell containing variable boundaries. The variable boundaries must be in continuous cell, either on the same column or in the same row, and they must be continuous. Number of division for the exhaustive search method, let's say 10 divisions, and let's select our output location. So from the exhaustive search method, we had our minimum value of x, that is our pressure P2 to be 0.7, and it occurred at, and its work is 236.6475. And if I'm to add the interval halving method, the cell containing the function variable, the cell containing variable boundaries, the output location. So I click on solve. So from the interval halving method, we also have 8 iterations with the minimum value of the function to be 235.8006, and it occurs at a P2 value of 3.161011. So that is for the direct search method. Now if we come to the gradient method, so with this objective function, and since this function was written in terms of the variable P1, that is the lower boundary of the variables, if you run the neutral option method, it asks for the cell containing function. So sorry, that is this cell. It asks for the cell containing function variable, and since it was written in terms of P1, we select P1. That means that 1 is the initial point of iteration. So the function, the output location, let's select here. So The annuity ramps in after 6 iterations give us the value of the pressure, that is P2, to be 0.162291. So we use this value to find for the work done. Yes. And the second method also asks for the cell containing function variable, the cell containing variable boundaries, maximum iteration, I will keep it at 100, output location, I will select here. I think that goes way down. So after 45 iterations, we have the objective function value for P to be 3.16.